So this right here is a problem from the 2024 MIT Integration Bee, Semifinals 1, and I think this is question 2. So if you go look at it, then you'll see that this integral is from there. Now, this guy right here looks kind of bad from the beginning, right? Because you have this quotient and the denominator is additive, but there's one trick that if you know it, you're home free, and that is the geometric series. So the geometric series 1 over 1 minus x is equal to the sum and then x to the n. It's pretty basic. Now x does have to be between -1 and 1. So see here that our denominator sort of looks like this. We can go ahead and apply it straight up. Except there's a couple of differences. So up here, see how this, here you have a minus x. Here we're adding on this variable term, e to the negative x. So to turn this guy, our formula, from a negative to a positive, well, let's plug in a negative x on both sides, where an x is. On the left-hand side, a negative x is going to cancel, give us a positive. On the right-hand side, negative x to the n can distribute onto the -1 and the x. All right. Okay, the second condition that we have to apply this, this variable term has to be between -1 and +1. So is that true here? Well, when x goes to infinity, well, e to the negative infinity is 0, and 0 is obviously well on that interval. Okay, for the other extreme, when x is equal to 0, almost, because e to the 0 is 1. If you take the limit, however, then it works out fine. So we're going to go ahead and treat it like that. So we can go ahead and straight up apply this formula to that right there. So here's what we're going to get. I'm going to copy down this integral on the outside. And then the numerator is going to stay here for now. We'll deal with the denominator for now. So we're going to start at n equals 0 and go to infinity. Now this is going to be alternating, as we saw earlier. Okay, and then we have this denominator part to the nth power. Now e to the negative x to the nth power, the powers combine. So you have e to the negative n times x. All right, and then you have a dx to close it off. Now we're going to do some shuffling. Okay, first this guy right here can come inside. And then we can switch the order of the sum and the integral. So the sum is going to be the very first thing you see. All right, it's going to be on the very outside now. Okay, and then we have the integral running from 0 to infinity. And I'm just going to write the rest of this stuff down. We have x times, here you have an exponential, there you have another exponential. So you can combine the two arguments. You have e to the negative 2x minus nx. Factor out a negative x, you get negative x times, you're left with the n and you're left with the 2. So you have n plus 2 dx. Now how about the -1 to the n? Well, it was originally going to go inside of the integral. However, this guy right here is independent of x, right? It's just a constant, so you can just straight up move it outside and it's not going to matter. Like that. So now this integral is so much easier to solve. It's just a case of integration by parts, and for that I'm going to use the DI method. Obviously you want to differentiate x because it's eventually going to go to 0. You have to integrate this exponential. Now, integrating this, you can use the reverse chain rule. If you want to think about it like that, it's just a u substitution where this top part is u. When you integrate that, you're going to get a new factor of -1 over n plus 2 on the outside, and then the exponential is going to repeat. Okay, but we have to integrate it twice, so the same thing is going to happen the next time, okay? This exact factor is going to drop out again from integrating this. So what does that mean? Well, the negative from this one and the negative from the new factor are going to cancel out, so you're left with the positive. And then the denominators combine. So you have n plus 2 times n plus 2. N plus 2 squared. Okay, and then e to the negative x times n plus 2 is going to repeat. So you're left with this diagonal, that diagonal. they are going to multiply, and then you have to integrate the row, but that's not really necessary because this is a factor of 0. That's going to give you 0. So let's go ahead and try to evaluate this. The first term is going to be negative. The x is going to multiply on. You have n plus 2 in the denominator, e to the negative n plus 2. Now, okay, let's just deal with this first term for now. Plug in 0 to infinity. When you plug in 0, I think it's pretty obvious it goes to 0 because this factor of x is going to zero out the whole expression. When you plug in infinity, it's a little bit more ambiguous because here, this x gets you infinity, but this e to the negative infinity gets you 0. So you have a 0 times infinity situation, which is indeterminate. But there's a few ways you can think about this. You can use L'Hopital's rule by dropping this into the denominator. The quickest way to do this is to notice that the exponential, it grows way faster than a linear term. So in this case, it's going to decay to 0 much faster than this linear term. So that means this entire thing is actually going to collapse to 0. So this entire first term is going to go to 0. So that's great. All right, so now let's evaluate the second term right here. Minus 1 over n plus 2 squared, and then e to the negative x times n plus 2 from 0 to infinity. Okay, plug in infinity, e to the negative infinity goes to 0, so it's going to zero out the whole thing. So that means all you're left with from this integral is just plugging in this 0. So let's subtract off. So remember how this works, right? Plug in the upper bound, subtract plugging in the lower bound. When you plug in the lower bound, this exponential is going to go to 1 because e to the 0 is 1. So you just have negative 1 over n plus 2 squared left. Okay? So what does that mean? The entire integral is equal to positive, because these negatives cancel, 1 over n plus 2 squared. So let's write that in. And that's a pretty nice simplification. And this also gives you a hint about where we're going next. So we have the sum going from n equals 0 to infinity. Okay, negative 1 to the nth power times this right here. So I'm going to write the negative 1 to the n in the numerator, and then the rest of the stuff below. All right, n plus 2 squared. All right, from here, I'd rather see an n squared than an n plus 2 squared, right? It's just more standardized. So I'm going to change the index from n starting at 0 to n starting at 2. So when n starts at 2, then right here, okay, the denominator is going to start at n. All right, it's going to just be n, sorry. It's still going to start at 2, but it's going to be n. The numerator actually doesn't need to change. Why? Because, so right here what this does is it's first positive, because negative 1 to the 0, then it's negative, then it's positive, then it's negative. This alternates, okay? And we still want this to start positive, and when n equals to 2, it still does, because negative 1 squared is just 1. So we don't need to change that. All right, so that is the form that we are now going to deal with. So I'll write this down above. And then I'm going to remind you of a certain function that you might or might not have worked with, but is completely related to this. Okay, so from here, the special function that I was talking about is known as the Dirichlet eta function. And that is notated using a Greek letter eta. And usually we have argument s. And this is defined as the sum, going from n equals 1 to infinity, of negative 1 to the n minus 1, n to the s. So, this already looks really similar to this, all right? There are a few differences though. And first main difference is the indexing. Here we start at 1, but in our problem we start in 2. So the solution is pretty simple. Let's just rewrite that, okay? So we're gonna have the sum start at n equals 1 instead. And then it's going to be the same argument for now. So problem solved, all right? The index is now the same as this. But to change the index from 2 to starting at 1, we added on the n equals 1 term. So we have to subtract it back off. Okay. So to subtract it back off, we have to figure out the value of it. And to do that, we just plug a 1 into n. Up here, we get a negative, and then in the bottom, trivially, this becomes -1. All right, that's pretty obvious. So that's just a +1. All right, so we have that. All right, and there is one more thing we need to do, and that is to introduce this negative sign in the power. Well, I think that's also pretty easy. I'm going to write the 1 plus first. So I'm going to 1 plus. Okay, so let's just introduce that and see what happens. N equals 1 to infinity. All right. So the effect of introducing this -1 is just flipping all the signs, right? Notice that if you do this, it's equivalent to just dividing a -1. See, if you just take this and divide a -1, then you get this. So to cancel that out, to cancel that effect and keep these equal, we have to multiply -1. And we're going to do that by changing this positive to a negative. So that's really simple. So this right here is just 1 minus, and this remaining sum exactly matches the form of the eta function, where s is 2. So this is just eta evaluated at 2. But what use is this function if we don't know the values of it, right? So that's where a very similar function comes in, and that's the Riemann zeta function. And this one is much more famous, and it has some results that people like know pretty much by heart as well. So we have the same indexing. The denominator is n to the s as well, but the numerator does not alternate this time. So it's just the eta function, but without the alternating. And these two functions are connected in a very specific way. If you go ahead and expand these out, so let's actually do that right now. So if you're, okay, so to preface this, if you're participating in the integration bee, you should probably know this formula already, so it doesn't take you all this time to figure it out. But for now, I'm going to derive the formula, because A, I can't remember it by heart, and B, you guys probably don't know it either. At least, yeah, that's what I'm assuming. So let's go ahead and derive it. And to do that, we expand both out, right? This one, to expand it out, just do the math in your head. You get 1 over 1 to the s, minus 1 over 2 to the s, plus 1 over 3 to the s, minus 1 over 4 to the s, and then dot, dot, dot. This one is the same thing, but once again without alternating. So it's just this. All right, and then once again, dot, dot, dot. How do you get from this guy to this guy? Well, if you go ahead and subtract 2 over 2 to the s, okay, and then subtract 2 over 4 to the s, and do this for every single even term, okay, what happens? Well, when these two combine, we get -1 over 2 to the s, okay, and when these two combine, you get -1 over 4 to the s. So basically, you take zeta of s and then just subtract by this, okay? You subtract by 2 over 2 to the s, plus 2 over 4 to the s, plus 2 over 6 to the s, and so on. So how do we write that function? Well, we see that if we take, it looks sort of like the zeta function as well, all right? First, you have to multiply this guy by 2, pretty obviously, because that way that'll introduce the 2 on the top. Okay, so this guy is just, I'll write it out now. 2 over 1 to the s plus 2 over 2 to the s plus 2 over 3 to the s. Okay, and then so on. Okay, and then you have to multiply on another function, which is 1 over 2 to the power of s. So the effect that that'll have, you're basically just dividing by 2 to the s. Okay, and then the effect that will have is this 2 to the s, when you distribute it over in the right-hand side, it's going to combine with all of these bases and multiply them each by this 2 right here. So the first term you get 2 over 2 to the s, plus 2 over 4 to the s, plus 2 over 6 to the s, okay? So that's just what happens when you multiply this 2 to the s in. All right, and so on. So we're going to, and earlier as we saw, to get the eta function, you take the original zeta function, all right? And then you subtract off this sequence right here, which we found was 2 over 2 to the s times zeta of s. So we had made the connection that if you want eta of s from zeta, then what you do is you take this guy, from it you subtract this. So I'm going to rewrite this slightly as, I'm going to combine this 2 with the thing in the denominator, so it's going to become 2 to the s minus 1 times zeta of s. So like that. And you can actually rewrite that pretty nicely by factoring out a zeta of s. And what you get is zeta of s times 1, right, minus 1 over 2 to the s minus 1. So that's the result. Okay, so now what? Well, we know the eta function in terms of the zeta function now. Let's go ahead and just straight up apply it to our situation right here. So from here, to rewrite the eta function, I'm going to use this exact formula we just found. Okay, so we're going to use this. Zeta of s, which is 2, times 1 minus 1 over 2 to the s minus 1. Now now s is just 2 because this is eta of 2. So if we plug in 2 there, we get 1 minus 1 half, and that's just 1 half. So in actuality, we can rewrite this whole thing right here as 1 half times zeta of 2. So that's what I'm going to do. Okay, so we're done using these two. All right. Now, zeta of 2 is pretty famously pi squared over 6, right? And that's known as the Basel problem. And I've gone over that twice on my channel before. So that'll be in a card that's in the upper right-hand corner of the screen. So yeah, this is right here is pi squared over 6. And you're wondering how would the competitors know that? Well, okay, it's a pretty famous result. So obviously, if you're competing in the prestigious MIT integration bee, you probably should know that, right? So anyways, yeah, this one is going to stay. You're subtracting off. When you multiply 1 half by pi squared over 6, you get pi squared over 12. That is very trivial. And that is your final answer. So yeah, there you go.